Hey guys, how's it going? Lehigh Nation. Um, I was going to continue on with calculus today, just because I love calculus. More specifically, or more generally, actually, it's calculus and vectors. Um, Now, I'm going to start off I'm in a very easy part of the course, right? So in this part of the course, basically, you have to calculate average rate of change, which is ARC. This is average rate, right, of change. And then IRC is instantaneous rate of change. Okay, so these are very simple. And I'm going to drop a little formula. So you're given a function f of x, okay, over some interval a, b. The average rate of change is basically the following. F of, let me do this, f of b, okay, minus f of a divided by b minus a. Very much a y2 minus y1 divided by x2 minus x1. That's it. That's all it is. So essentially all I'm going to do is plug in values. So I know that f of x, right, equals x to the 4 minus x cubed plus x squared. So the average rate of change, right, for this question, 11a, over an interval negative 1 comma 1 equals the following. It's negative 1 to the 4 minus negative 1 to the 3 plus negative 1 squared, right, all in one bracket. Okay, so that's f at b essentially, or f at or f at positive 1 actually, sorry. Positive 1 comes first, so that's gone, that's gone. So f at 1 minus f at negative 1. And so I do blah, blah, blah. Okay? All over b minus a, so it'd be 1 minus negative 1. Done. So I evaluate. 1 minus 1 plus 1, that's 1 minus, and I get 1 plus 1 plus 1, so 3. Okay? And then I get 2 on the bottom, so I get negative 1 as my final result for the average rate of change. I do the same thing for this function, right? Oop, let me erase this a little bit. I do the same thing for this function over an interval 0, 2, and a in this case is 0, b in this case is 2, and then I do that, right? So there's nothing new here, nothing to be afraid of. And then for instantaneous rate of change, it's not as straightforward, I think. Instantaneous rate of change needs a little bit more work, or not more work, but more thinking. Okay, so instantaneous rate of change is the slope, if you will, at a given x value. Now, for those of you that probably could guess, this is the derivative essentially. But before you actually do derivative rules and first principles, you can evaluate the derivative at a certain x value by coming really close to the specific x value. So what I mean is, in 12a, x equals 1, right? So I do that same formula where I've got like f of b minus f at a over b minus a. I do that same formula, but I come really close. If a is 1 in this case, right, this guy is going to be like 1.01 or something like that. And so, the IRC would be like, f at 1.01, 1.01 minus f at 1 over 1.01 minus 1, okay? And I use this function, okay, and I plug those in, right? So it'd be 1.01 to the 4 minus 1.01 to the 3. Okay, I've just basically used this function, plugged in 1.01. Take away, okay, remember always use brackets, guys. 1 to the 4 minus 1 to the 3. That's it. Okay, all over 1.01 minus 1. I evaluate and I've got my instantaneous rate of change. It is that simple, nothing that bad, right? Not that bad. So if you, we would like kindly support your support. If you could like comment, like, subscribe, share videos. We love doing this. It's always fun to do math. I love math. Math has helped me through some tough times. Some of the stuff just makes me so happy. Now in this case, we have, instead of average rate of change, it's average velocity, but guess what? It means the same thing. So these guys are position functions. Okay, they don't tell you that, but those are position functions. So there's no real difference here. I mean, position function over some set of time, right? That's velocity, okay? So you got to do a ratio of stuff. And it's the same stuff that we were doing before, where you go, this time instead of f of b minus f of a, it's s of b minus s of a over b minus a. That would be the average velocity. Average velocity, AV, I'll just call it that. And so in this case, it would be like a is 0, b is 2, right? So it'd be s at 2 minus s at 0 over 2 minus 0, okay? And so in this case, it'd be, let's see, 2 squared plus 2, 6, okay, minus s at 0 is 0, right? Over 2, it's 3, okay? So that's the average rate of change. The instantaneous rate of change, let's say for 14a, right? This is 13a, okay? 14a, the instantaneous rate of change, same thing as before, right? So it's kind of like the average rate of change, except this b value is very close to the value they want, and we call this value the a value. So it'd be like 1.01, okay, minus s at 1 over 1.01 minus 1, all right? The smaller you get, or the closer this value is to the a value, the better your answer, right? Or the more accurate, I guess, your answer. So I could have even used, 1.001, for example. But I'm not going to do that. But anyway, 1.01 squared minus 1.01. Okay, that's s at 1.01 minus 2 times 1 squared, okay, always put brackets, minus 1, okay, all over 1.01 minus 1, evaluate, and you got your answer. Done. Very simple. Okay, now this is more fun stuff for me. I love this stuff. This is first principles. Now, first principles is a limit, okay, as h approaches 0. It's basically the derivative function, right? The derivative function. A limit as h approaches 0 of f of x plus h minus f at x over h. Okay. So for example, let's use let's use 1b. Okay, I'm not going to jump with 1a because 1a is a constant function. And I might well, okay, let's do 1a. Who cares? Okay, I didn't want to lose you, but okay. F at x is equal to 3. Okay, so that goes right here. That goes right there. Okay, so what's f of x plus h? Well, for a constant function, I plug in anything for my input, right? This is the input. If I plug in anything, I get 3. That means that f of x plus h equals 3, right? So all I have to do is evaluate what this ratio is, and then stick in this limit of h approaches 0, and then I've got my derivative. That's it. So I already know what f of x plus h is. I know what f of x is, so I just do the ratio, right? And I always do a difference first, because it makes things easier, right? Watch this. 3 minus 3 equals 0. Then I stick an h in there, okay? Still 0, right? Because no matter what I plug in, 0. So I get 0, and now I'm good, okay? And now the limit, so the derivative would be the limit as h approaches 0, right, of this, which is 0. And I'm done. That's it. That's part A. So I guess it wasn't too bad. I shouldn't have shied away from it, that's for sure. Let's see. hate the erasing part, just because I know it takes so long. But thank you for sticking with me, sticking with us, sticking with Lehigh. Okay, so we've got f of x equals negative 2x plus 5. All right. Okay, now this is where I lose some people. This is input. This is an input, right? And it says take negative 2, multiply by the input, and add 5 at the end. Now it's saying the input is x plus h. Whenever you have a new input that's like longer than just one letter, just put brackets, right? So the input is the same. Multiply by negative 2 and add 5. Okay? So I'm going to evaluate this. This is going to be, I'm going to expand negative 2x minus 2h plus 5. Now when I do this, f of x plus h minus f at x, right? This and this will for sure cancel, right? No point in writing it out. The 5 and 5 will cancel, and then all I will get is a negative 2h from here, okay? Now all I do is divide by h is cancel, and I get negative 2. This must mean, right, if I tack on a limit as h approaches 0, that my derivative will in fact be negative 2. You can try it yourself, okay? So that's what I get. I'll do one more example out of these guys, and I'm going to move forward with differentiability, which is essentially checking the whether or not something has a kink or anything like that in the actual plot. Okay, I'm gonna go with, let's see, E. And you'll see with E, there's this, when we evaluated limits, there was conjugation method. It's basically that, right? So f of x plus h will be, so it's saying take the input, which is x in this case, and square root it, right? So the input is longer, right? It's going to be x plus h, so square root that. That's it. So f of x plus h minus f of x, right, will be square root of x plus h minus square root of x. Done. Okay. Now just put it over h. Actually, let's not do that yet. Let's do conjugation. Okay. So take this guy, right, and multiply by the square root of x plus h plus root x, root of x plus h plus root x. And the reason why I'm doing this first is because at the end I can just like tack on a h on the bottom, and then we're good. All right, notice this is a minus b, and this is a plus b. That will make a difference of squares, a squared minus b squared, which just happens to be x plus h minus x. Okay, try it for yourself. X plus h plus root x. All right. Now, x's will cancel, and I'll get just h at the top, right? So I'll just get h at the top, so I'm just going to put that in, h at the top. Now, divide everything by h, so that amounts to putting an h on the bottom, and I can cancel the h's, and I get 1 over this thing, right? Now, if I set h approaches 0 to get my derivative, then my derivative, f prime of x, will be, let's see, 1 over root x, right, plus 0, that's just root x, plus root x. And so I get 1 over 2 root x. Done. All right? You can do the same thing with this example. Of course, it gets a little messier. You might need like a difference of cubes, a difference of squares, who knows. You might need to factor it if it's factorable. But either way, it's this sort of work that I love it. I think it's really great. Okay, let's see, differentiability. Let's see if I can answer this. Whenever a limit doesn't exist, I mean, whenever you get like a jump like this, you definitely can't differentiate. If you get a kink like this, you cannot differentiate. If you get like some sort of absolute value behavior where like the slope sharply changes like that, you cannot differentiate. So I'd identify -2 where you cannot differentiate, -3, where you cannot differentiate, and 1, x equal to 1. So x equal -2, x equal -3, x equal negative, oops, did I say them all? I think I did. Yeah, where they cannot differentiate. Okay, let's see. We can even do some power rule, right? Sorry, that was my clock. My clock's going off. Sorry, guys. But yeah, this looks like so much fun. I love this stuff. Okay, now the power rule to differentiate. Okay, so the power rule says that whenever we have a function x to the n, that the derivative, okay, is going to be nx to the n minus 1. Okay, now, so that translates very easily for certain functions, right? So for 3a, right, I've got f of x equal to x, but that's just x to the 1. So n equals 1, so I just use my formula, right? So f prime of x is just going to be 1 dot x to the 1 minus 1. That's x to the 0. X to the 0 is 1. So it's going to be 1 dot 1 equals 1. So you just memorize, whenever you see f of x equal to x, the derivative is always 1. So the derivative of f of x equals to nx, any number times x, so it could be like 2x, 3x, 4x, it's just the number in front, right? So that's the derivative of f of nx. Remember that, okay? So for instance, you know, f of x equal 3x, the derivative is just 3. F of x equal to 4x, the derivative is just 4. F of x equal to 5x, the derivative is just 5. F of x equals to 1,000,000x, the derivative is 1,000,000, okay? Just pick out the number. So f of x equals to x is 1x, f of x, so the derivative is 1. Very simple. Okay, so with that being said, you know, f of x equals to x squared. N in this case is 2, right? N equals 2. So the derivative, f prime of x, should just be, and by the way, this is part B. Okay, the derivative will just be 2x to the 1, right? Or just 2x. C, let's see, f of x equals x cubed. Derivative, f prime of x equals 3x squared. Okay. D, f of x equals x to the 0, okay? Now notice, you know, what you would do is you would write, if you're going to use the rule, you would just write like f prime of x, bring the 0 down, you know, x to the -1, that's just 0. But really, all you have to do is just notice that x to the 0 is 1, which is a constant. The derivative of a constant is always 0. That's it. Okay, so let's see, E f of x equals x to the -1. Bring the -1 down, okay, and you end up getting -1 over x squared. Okay, let's see, f. Normally I see this a lot where they don't put it into a power that you could use right away for the derivative. They give you like a quotient like this. You have to change it to this form, okay? Now to do that, you put a negative on the 2, and that's equivalent, right? So these are equal. Now, with this being said, the derivative is going to be, okay, x, -2x and -3, so -2 over x cubed. Done. Okay, now these square roots are or you know, cubed roots, these are a little different. And they require a little bit more, they require a little bit of reorganization before you actually continue on with the derivative. But yeah, let's see, I'm just erasing. Hopefully I'm not boring you guys too much. I love doing this stuff so much. It really helps me with my depression and anxiety, believe it or not. Doing this stuff, helping you guys, if you need it, helping you guys makes me pretty happy, actually. We got a square root of x, okay? We rewrite that as x to the 1 over 2, okay? So remember that. Now then the derivative is going to be 1 over 2x to the negative 1 over 2, because that's 1 over 2 minus 1. 1 over 2 minus 1 equals negative 1 over 2, all right? And that's just because 1 is 2 over 2, right? So 1 over 2 minus 2 over 2, that's negative 1 over 2. So we end up getting, if we simplify it, it's 1 over 2 root x. I usually remember this, you know, f of x is root x. The derivative is going to be 1 over 2 root x. I usually just remember that. It's really helpful, especially when I'm tutoring students, right? Now we've got the cubed root of x. The derivative, it can be rewritten. Okay, I'm going to rewrite it before I do the derivative. It's going to be x to the 1 over 3. So f prime of x is going to be 1/3 x, okay, to the negative 2/3. Okay, and that's because 1 over 3 minus 1, or 3 over 3, is negative 2 over 3. And so I end up getting 1 over 3 cubed root, notice that's a cube, not 33, right? That's a cubed root of x squared. And that's what I get. And lastly, this is a little different. Actually, it's a lot different than h when you think about it in terms of powers. F of x equals to the square root. So notice this was the cubed root of x. This is the square root of x cubed, different, right? This is rewritten as x to the 3 over 2, right? Because square means 2, right? So 3 over 2. And so the derivative is 3/2 of x to the 1/2, which can be written as 3 root x over 2. Done. Okay. Now the rest of it is a general differentiation that I'll have to go through. I think I would have to go through in a different video just so I can explain what's going on. And then afterwards we're going to do some neat stuff with the equation of the tangent, maybe some implicit differentiation, more general differentiation that might involve, you know, chain rule. For example, we've got some chain rule stuff that I'm going to do. Generalized differentiation rules, finding first and second derivatives, right? Now we're going into concavity, critical values, derivative signs, derivative tests, stuff like that, local extrema, absolute extrema, intervals of concavity, right? Points of inflection. Points of inflection are when the second derivative is equal to 0. So nothing but fun stuff ahead, and then afterwards, the stuff that I've really been waiting for is vectors, right? So this is the vectors section, and I will actually be covering that. I'm actually super stoked about it because I did a physics degree. So this stuff is going to be heck of fun, right? Sorry, I don't say hell. I'm LDS, but anyways, thank you so much for watching. If you can, please comment, subscribe, share with your friends, right? If they're having trouble with calculus at all, if you have special requests too, let me know, and you know, just send me in a PDF or something so I can get working on it, and I can, you know, throw you some videos out there with some audio so that you can follow along and I can answer your specific questions. So thanks so much. Have a good one, and I'll see you next time. Bye.